Hi students, today we are discussing purification of crude metal by vapor phase refining, electrolytic refining and chromatographic methods. Vapor refining, vapor phase refining nothing but purification. Why vapor phase means here we are converting metal into vapor phase. That's why we are calling vapor phase refining. We have two vapor phase refining methods, that is Van Arken method. Van Arken method. Van Arken method. Van Arken method is vapor phase refining method. To get ultra pure metals, we are using Van Arken method. And here what we are doing is impure metals are converted to volatile stable compound. Impure metal converting into volatile stable compound. Volatile stable compound. Volatile stable compound. So here compounds we are converting into volatile, means which are ready to evaporate. That's why vapor phase method we are applying. And impurities are not affected. Where impurities are not affected. When we are converting impure metal to volatile stable compound, impurities are not affected. And later, volatile compounds subjected to decomposal by using current, means electrically these are going to be decomposed. Then we are getting pure metal. So first what we have to do, impure metal is subjected to convert into volatile stable compound where impurities are not affected. Next, volatile compound are decomposed electrically to get pure metal. This is Van Arken method. By this method, we are refining titanium or zirconium. Metals like titanium or zirconium are subjected to purified by this method. So what we have to do? Step 1. Impure metal has to subjected to convert into volatile stable compound. So this titanium is subjected to treat with iodine. Subjected to treat with iodine at 500 degrees Celsius temperature, 500 Kelvin temperature. Then titanium react with iodine form titanium tetraiodide. Titanium tetraiodide. This is titanium tetraiodide. This is volatile stable compound. This volatile stable compound, titanium tetraiodide, subjected to heat at high temperature. At high temperature, titanium tetraiodide subjected to heat at high temperature. That is nearly 1700 Kelvin temperature. Then these are decomposed. These are decomposed into titanium and iodine. Titanium and iodine. So this is we have impure and subjected to treat with iodine, titanium tetraiodide. This titanium tetraiodide subjected to heat at high temperature, and we are getting pure titanium metal. This is impure, this is impure, and this is pure. This is pure. And this is the method we have, very useful for removing, impurities such as oxygen and nitrogen. This you have to remember. This is the method we have, very useful to remove oxygen and nitrogen completely. Next, another method we have, that is Mond's method. Mond's method, or we are calling Mond's process. Mond's process. This is also vapor phase refining method. Here what we are making refined means nickel. Nickel metal is subjected to refine, impure metal is subjected to refine by vapor phase refining. Impure nickel treated with carbon monoxide. Impure metal subjected to treat with carbon monoxide. So here Van Alkyl, impure metal subjected to treat with respective compound or metal or non-metal to get volatile stable compound. Here impure metal subjected to heat with carbon monoxide, forming volatile compound. So in both Van Alkyl and Mond's method, we are getting volatile compounds. This volatile compound further decomposed at high temperature, then you are getting pure metal. So let me discuss the reactions which are involved in Mond's method. So here reaction number 1, nickel is treated with, this is impure, carbon monoxide subjected to heat nearly 330 to 350 Kelvin temperature. Then you are getting nickel complex, that is tetracoulomb or nickel tetracarbonyl. This is we are calling nickel tetracarbonyl is a complex, and this is we are subjected to heat again. Nickel tetracarbonyl, nickel tetracarbonyl at high temperature, nearly 450 to 470 Kelvin temperature. It is a decomposed, and you are getting nickel pure metal, and carbon monoxide is subjected to removed from the complex. So this is Mond's process we have to get pure metal of nickel. Next, electrolytic refining. Electrolytic refining. Electrolytic refining. Why we are calling electrolytic refining means here we are using electricity to make the process. What type of metals we are using? Refining means copper, silver, gold, zinc, aluminium. Like metals are refined by electrolytic refining. And here impure metal act as anode. Pure metal act as cathode. Electrolytic solution, same metal, electrolytic solution act as electrolyte. Impure metal act as anode, pure metal act as cathode, same metal solution act as electrolyte. How it will be work? Look here. This is the electrolytic cell we are using. We have to take impure metal as anode. This is the impure metal rod. I am taking impure metal rod. It has anode, means positive terminal, and we have pure metal. This pure metal act as cathode. These two are connected with a battery. Impure metal act as positive terminal, pure metal act as negative terminal, means anode and cathode. Same metal means the metal which we are refining. For example, copper we are refining means this is impure copper, pure copper. Silver we are refining means impure silver, pure silver. Gold we are refining means impure gold rod, and this is pure gold. And such metal solution we have to take. For example, I am taking, this is copper refined. This is copper impure. And this is copper pure. Copper pure. And here same metal, copper sulfate solution we have to take. Copper sulfate solution. Then when we pass electrical current, this is positive terminal, this is negative terminal. We have positive and negative. This is plus and this is minus. Then we are getting this impure metal rod release Cu2 plus ions. Cu2 plus ions by losing electrons. These electrons moving along with the circuit and moving towards here cathode. This is cathode, this is anode. Then ions moving into the solution, and this plus 2 ions are attracted by this cathode. Why? Because positive attracted by negative. And these copper ions are subjected to form as a layer on pure metal. As the time passing, anode metal, that is impure metal, size is going to be decreased. Cathode metal, that is pure metal, size is going to be increased. Means Cu impure converting into Cu2 plus ions by losing 2 electrons. These are attracted by cathode. These are attracted by cathode and converting into copper metal. Converting into copper metal. This is attracted on the cathode. This is electrolytic method. We are to refine by electrolytic refining method. Next, another method we have here, that is Parks method. Parks method, that is PRKS, Parks method. Here silver or gold which is associated with lead impurities, silver or gold which is associated with lead impurities are subjected to purify by Parks method. What happened here means this impure silver or gold which is associated with lead is treated with zinc. Impure metal treated with zinc. For example, if silver associated with lead impurities, this is treated with zinc. Zinc ready to react with silver, but zinc can't react with lead. Reactivity towards silver, zinc reactivity is more than lead. That's why zinc we are taking as reacting substance. So impure metal is subjected to treat with zinc. Then what happened here means this method, this zinc is going to be react with silver, then we are getting silver zinc amalgam. What we are getting? Silver zinc amalgam. Sorry, we should not say amalgam, mixture. Zinc silver mixture we are getting. Means zinc is ready to miscible with the silver, but zinc is not ready to miscible with lead. Now zinc and silver mixture we have. It is subjected to heat, and this is having some volatile nature. Or zinc having volatile nature. When we heat this mixture, silver is separated. Silver is separated out, and zinc is removed as again impurities. Like that, we are removing lead from silver impure or gold impure. So zinc separated by distillation. How can we remove zinc? By distillation. By distillation method, we can remove zinc and silver is separated out and pure silver you are getting. This is the method we have. Impure silver or gold is separate or purified by patch method where lead impurities are present. This impure metal is treated with a metal zinc. Zinc is ready to react with silver or gold but not with lead. Then this mixture is subjected to heat, and zinc having the nature to volatile. So that is by distillation. Then zinc is separated. Silver is separated. This is the method we have. So that is Tuck's method. Next, we have chromatography. Chromatography is the technique we are calling as a modern technique. Completely modern technique. By this method, we can purify impure metals. What the principle here included means different components of a mixture. Different components of a mixture adsorb differently. See here adsorption process. By this method we can purify. Here we have to take a column, and this is looking like burette, which we are using in our lab with a tab. We are using column. That's why this is we are calling column chromatography, and it is subjected to fill with silica gel. Silica gel as a adsorbent. Silica gel as a adsorbent. So it is fitted with silica gel. Total silica gel we have here. Total active silica gel which is worked as adsorbent. Then impure metal is introduced into the column. Metal solution means molten form. If we impure metal having X and Y means X may be pure, Y may be impure, like that. These two are having different absorption capacities. Then when introduced the molten impure metal, the particles that is impure or pure which are having less absorption we can connect here first, and which is having more absorption capacity later will connect. Means first it will be absorbed here in this more absorption capacity that will be absorbed here. More absorption capacity, less absorption capacity that will be absorbed somewhere here. Less absorption capacity. That's why this will be collected first, then more. So this is a modern technique when different components of a mixture having different absorption capacities. Silica gel we took here as absorbent, or any aluminum also we can use. Absorbent we can use as a alumina also. Alumina also act as adsorbent, not only silica. Like this we can separate out by using this technique. Next, we have another concept, that is thermodynamics principles of metallurgy. Thermodynamics principles of metallurgy means thermodynamics principles we can apply here in metallurgy for reduction process. What principles we can apply here means, Gibbs energy. This Gibbs energy we can use here. Gibbs energy concept of thermodynamics helps to understanding better about metallurgy. You know the formula, that is delta G equal to delta H minus T delta S. Very important thermodynamics formula. Delta G gives a change in the Gibbs free energy, and delta H is the enthalpy change. Delta H is equal to change in the enthalpy change in enthalpy, and similarly delta S, change in entropy, change in entropy, and pre-temperature delta G is Gibbs free energy, change in the Gibbs free energy. And if delta G equal to 0, the reaction is in equilibrium. Reaction in equilibrium position. If delta G value less than 0, nothing but negative. Less than 0 nothing but negative. Then reaction is spontaneous. If delta G value greater than 0, that is the value we are getting positive, and the reaction is non-spontaneous. Spontaneity and non-spontaneity means in thermodynamics, delta G value when reaches to 0, that is negative, then that will be reduced. And if it is positive, delta G value, that can't reduce. That is about thermodynamics principles where we are using in metallurgy. Delta G equal to delta H minus P delta S, where delta G gives free energy, delta H equal to change in entropy, delta S equal to change in entropy. Delta G reaches to 0, reaction is in equilibrium. Delta G less than 0, negative, spontaneous, and here positive is there, non-spontaneous. Delta G reaches to negative, that is reduced easily. Positive can't reduce, means we have to use reducing agent. In the presence of reducing agent only, that will be reduced. Normally it is not reduced. Okay.